But now let's focus on the direction of acceleration. So what we find here is that, again, we're going to use your body. Again, we use your body's motion to determine the direction of acceleration. And here we go. Now note that this is only valid if we're speeding up or slowing down. If we're turning, it's more complicated. Okay, it's definitely more complicated. So here's what we know. The direction of acceleration is always opposite to your body's motion. So let's look at the two situations. So if you're looking at slowing down, so if you're slowing down, you could imagine that you have your car. And what happens when you're slowing down, you're seeing here that your body, as we've already talked about, is moving in the forward direction. So if your car is going forward, we know that the direction of your body goes in that direction. So then this tells us here that the acceleration is in the opposite direction. I can do the same thing for speeding up. So if I'm speeding up, again, I look at my car, and so when I'm looking at my car, my velocity is again going to the right. So when I'm looking at the driver's body's motion actually goes into the chair. Therefore, the acceleration must be in the forward direction here. So I can then draw these a little bit more, easily without all this stuff here. And what we can see here is that we can summarize what we mean by this here. So then we could then say that if we have, so if my acceleration is in the opposite direction of the velocity, right? So we're seeing here that the acceleration is opposite of velocity, then we slow down. If the velocity is in the same direction as the acceleration. So then here, the acceleration is in the same direction of as velocity. Then we speed up. So that means we can now add acceleration to our language in motion diagrams. So now adding acceleration to motion diagrams, we have the following thing. So if I have constant velocity, right? So if I have constant velocity, we know that our arrows do not change. So what we can do here, we could now replace this guy with an arrow that looks like this. I could then say that I have a velocity that goes to the right, and that doesn't change. So the way I show that this doesn't change is I put acceleration equal to 0. That is the same thing here. Now, if I'm speeding up, we know that our arrows are changing in length here. So we can rewrite this to read as follows here. Let me move this over here a little bit because I'm going to run out of space. So then in this situation, we could say that another way to write this is to say my velocity is going like this, but my acceleration is pointing in the same direction as the velocity here. And then finally, we could talk about slowing down. Here, we see that our velocity vectors are getting shorter and shorter. Another way that we can write this here is to indicate that my velocity is still going to the right, but my acceleration is in the opposite direction. So that is one way that we can actually say this. Okay, now what we should do here is that we should talk about how we use the word acceleration in physics here. And here's where we get into tricky language. So now I want to talk about the language of acceleration in physics is different than everyday language. So what do I mean by this? If we are speeding up, we call this acceleration. If we're slowing down, we call this deceleration. Now, I'm not saying that that's not correct, and everyday language is definitely correct, but that is not how we define acceleration in physics. So so this is, like I was saying here, this is correct in everyday language. Oops, let me try that again. By definition, physics uses a different definition. Okay, it uses a different definition. And the way we do this here is we talk about using positive and negative acceleration. So here's what we do. The direction of the velocity is defined as the positive direction. And again, I think we've talked about this before. If you're driving from Santa Cruz to Cabrillo, is that a positive or a negative direction? On the other hand, if you're driving from Cabrillo to downtown Santa Cruz, is that positive or negative? What determines your direction should be the direction of the velocity. So the way we write this is we write it as follows here. We then say this, that our velocity is always in the positive direction, no matter what. Our velocity is always in the positive direction, no matter what. So then we pay attention to the acceleration. So relative to the velocity, if our acceleration points in the direction of the velocity, you can clearly see that this means positive acceleration. And that means that you are speeding up. So that's if you're going to the right. But here, now check this out. That seems to make sense right there. But wait a minute. What happens if I'm going to the left now? If I'm going to the left like this, and this guy is still the negative direction, and let's say that I have an acceleration that points in this direction, see how the acceleration and the velocity still point in the same direction? That tells you that you're speeding up still. So even though the velocity is pointing in the negative direction and the acceleration is pointing in the negative direction, that is called positive acceleration because the result is that you speed up. The same thing happens if I go the other direction here. So now if I point my acceleration in the opposite of the direction, we call this negative acceleration. And the reason why we call this negative is because no matter what, you slow down in this situation. You are slowing down. And what I mean by that, even if I move in this direction, where I'm moving in the negative direction, if I have an acceleration that goes in the opposite direction, this is still called negative acceleration, even though the acceleration is pointed in the positive direction. We don't look at what is positive and what is negative, is what is the acceleration relative to the velocity. And where you want to be careful here is textbooks will screw you up. There are numerous textbooks that will immediately tell you to do the following thing here. They're going to say, hey, what we want you to do is that I want you to tell me whether the velocity is positive or negative, or the acceleration is positive or negative. And for example, if we look over here to the bottom where we're speeding up with the velocity and the acceleration, they'll go like, oh, that's a negative value, that's a negative value. So I have negative velocity, negative acceleration. And then they'll say, you're speeding up. Regardless of your how you define positive and negative direction, just remember the acceleration only makes sense relative to the velocity. Like in this situation right here, you know what I would do right here? If I had this situation, that's like driving to, right? In this case, we could say that this is going from downtown Santa Cruz to Cabrillo. Wow, I can't even spell Cabrillo. Look at that. And I've been here, what, 25 years? Or is this Cabrillo versus downtown Santa Cruz? So what would I do in each of these situations? I would pick the top one, downtown to Santa Cruz, as the positive direction, and then I would purposely change my positive and negative sign down here and make the left positive and the other direction negative. So the language can get tricky here, but that's our language in physics here. So to give you a sense of what do I mean by all of this, what I want to do here is that I want to further emphasize this. To emphasize this, I'm going to look at the units of acceleration. Okay, so let's look at what do I mean by positive and what do I mean by negative. So here's what we're going to do here. We're going to, we always assume constant acceleration. In this course. If you do not have constant acceleration, then you have to, you must use differential equations, math 7, to solve these problems, which of course is beyond the scope of this course. So that means here is that when I look at the acceleration and how we defined it, this guy has to be a constant value. And what's going to be, clear here is that we want to pay attention to that delta V. This tells us how much the velocity changes per unit time. And that turns out to be the most important one. Okay, so let's look at some examples here. So the first one I want to focus on here is that I want to focus on positive acceleration. And you'll see why positive acceleration makes more sense here. So here's what I'm going to do here. So for this example, what I'm going to focus on is that I'm going to say that my acceleration is going to be plus, that means positive, 5 meters per second every 1 second. So what does this mean? Okay, so what we do here is that we're going to look at a motion diagram. So let's look at an object that starts at rest and has positive acceleration of 5 meters per second every 1 second. So now if I start to look at my motion diagram, what does this look like? Well, what this tells me here is that at 0 seconds, I know that my speed is 0. So if I start at 0, what does this tell me here? Well, I want to look at what happens at 1 second of time. According to this thing here, this quantity right here, this tells us by how much it changes. So here's what happens here. So now I'm going to look at the first point. Okay, so I'm going to look at the first point. So right here, I'm going to focus at this point here. And this is what I know. I know that my change in my velocity started at v equal to 0, and then it changed by this amount, delta v, over 1 second of time. So in this case, this is going to be 0 plus 5. So this will now be 5 meters per second. So when I go and I draw my arrow then indicates that this is 5 meters per second going to the right. What happens after 2 seconds now? Let's say that this is my 2-second mark. Well, this guy is 0.1 right here at 1 second. So now if I look at this point up here, what you're seeing here is that my speed has changed by that same amount, delta v, after 1 second. So I started off at 5, but I've now changed that by 5. So now it's 10 meters per second. So therefore, it's telling me by how much my speed is changing per unit time. And you can see here that if I look at 3 seconds, you probably already realize that this is then going to be my speed at 2 is then going to change by that same amount, which will then be 10 plus 5. So I now get 15 meters per second. So therefore, this guy gets longer to 15 meters per second. So you can see how that is changing in increments of 5. But it's this guy right here that's telling me. And you can see why it's useful to have that positive sign there, because it's adding to the speed. On the other hand, I can have negative acceleration. Looks like my tablet there's a lag in it. Hopefully that's not confusing you. It's definitely confusing me. So now let's look at this guy. So this acceleration in this situation, I'm going to say has a negative sign here. And here, I'll say that this is changing by 10 meters per second every 1 second. So again, let's assume that here, what I have here is I have an object that is already moving. And then we got to pick some value at moving at, let's say, 50 meters per second to the right. So this negative sign here becomes important. Why is it important here? Because it's telling me that, of course, that makes it negative. So instead of adding, it's taking away from the velocity. So then I go and I start my motion diagram again. So here's my motion diagram. At 0 seconds, we know that this thing is moving, let's say, at this length here, which is then be 50 meters per second. You know what I forgot to do this time? I forgot to say that this here is my acceleration of 5 meters per second every 1 second. I did not include that. So in this situation, I'm going to have acceleration in the opposite direction, which will be 10 meters per second every 1 second. So now what's going to happen here? Well, it's going to slow it down. So at 1 second, playing the same game as before, I then say that at speed 1, this is going to be v initial plus this change in velocity. You could see here is that I'm at 50 meters, but then I changed my speed by 10. So now I'm at 40 meters a second. So you're seeing here is that it is now the negative acceleration is reducing the speed at this point. And if I go to this point right here, let's say at 2 seconds, we could then see that if I look at this guy, this is going to tell me that at 2 seconds, it's going to be v1 plus this change in velocity due to the acceleration, which then tells me that this will be 40 minus 10, which will then give me 30 meters a second. And you could see how this is now slowing down. Acceleration. So that we can get a sense of what we have. So when we plot acceleration, it's very similar to plotting velocity or position. So what we know here is that from our definition of acceleration, our acceleration will always be a constant in this course. And this, by definition, is our change in velocity over our change in time. So now what I want to do here is that I want to make this, I want to convert into a linear line equation. So then I take 2 steps here. How do I take these 2 steps? I'm going to solve for delta V. So if I solve for delta V, you can see here that then this guy, and doing exactly what we did last time, I defined delta T as T. And so what you're seeing right here, that the acceleration, that this guy, the acceleration is the cause of changing velocity. Just by looking at that equation right here. So now, if I rewrite this as a linear line equation, I can then say the following thing here. I can then say that delta V is the same as V2 minus V1, which is then AT, which then I can rewrite this as V2 V1 plus AT. And this is my linear equation for velocity here. So now, let's plot this to get a sense of what we mean by this. So right away, what we're seeing here is that we're seeing this. What we're seeing here is that the slope of this line is equal to the acceleration, and this has to be constant. And then we see here is that our intercept is going to be V1. So let's look at how we plot this thing. So if I look at a graph like this, this is what I'm seeing here. You know what? I'm going to move this down a little bit. I need a little bit more space. I want to talk about speeding up here now. So if I'm speeding up, what do I know here? If I look at my velocity versus time curve, what I'm going to see here is that I have a line that's going to look something like this. So this line represents the line where there is no change in velocity. So this line here says V is equal to a constant. And if it's equal to a constant, that means that this line equals zero acceleration. So that means here is that in this situation, the velocity V1 has to be the same as the velocity V2 at this point right here. Now, if I speed up, that means here is that I have to change my velocity. And so I now have a slope that looks something like this here. And so when you're looking at this thing, this represents how velocity is changing, because this tells me that this is delta V. And this delta V, as we already said here, was equal to what? The acceleration times my time interval. That's how I change. So this here, this is my, I have an increase, excuse me, not an increase. I have a positive sloped line. So when I look at this guy, this tells me then that I have this situation. That if I'm increasing, then that means I have a velocity that's moving in this direction, in the positive direction, and I have an acceleration that's also moving in the positive direction. So when I look at my equation of a line here, this tells me that V2 is going to be V1, and then I'm going to have a positive acceleration to increase the velocity right there, where V2 is clearly larger than V1. And I did not mark this off, so this will be V2 right there. So that's what I mean by positive acceleration. So when I look at this graph here, and I plot acceleration, the fact that acceleration is positive, that means that my line shows that this is a constant. This shows that I have constant acceleration. So these curves are connected to each other because I have this flat surface on the acceleration versus time curve. On the other hand, I can also, I wonder if I can put this all on one. I don't know if I can. Let me see if I can move this over, because it would be nice if we had one picture of everything here. So let's see if I can fit in this other one here. So now this was speeding up. Now let's talk about slowing down. And slowing down means negative acceleration. And you could see that I messed up here and I didn't put that this was positive acceleration. So now let's do the same thing. So now here is my graph. And again, I have my velocity curve. And I like this here. And so what am I seeing here? What I'm seeing here is that I still have my same line. So my same line is this line right here. And I'm going to say that this line here represents my V equal to a constant here. And at this point, I'm calling this V1. So if I'm going to decrease my speed, that means I have to have a line that goes down to V2. So let's say that this line here is V2 and that this represents my point right here. So then what you're seeing here is that my line is going down to this point right here. So if I look at the same type of thing, again, this is my zero acceleration line. But in this situation, what you're seeing here is that there is a decrease in speed. In other words, in this case, over here, we had a positive acceleration. In this case, we see that we have a decrease. And the reason why we have a decrease here is that we have a negative acceleration in this situation. In other words, when I look at my velocity that's moving in the positive direction, this acceleration is pointing in the opposite direction. So equation-wise, this reads that V2 is equal to V1, and then I'm going to get my minus A times T. So you could see here that once again, the acceleration is about how we define speeding up and slowing down is only the sign of the acceleration. Where in this case, we see here is that where V2 is less than V1. So now if I plot the acceleration, what we're seeing here in this situation is that the acceleration is not positive, it's actually negative. This is a negative acceleration because not only does it point in the opposite direction, but it has a negative value to actually show that.